After the class, Abdullah, at 10:30. Okay, so up to last class, we have finished motion of charged particle in magnetic field. So those who were absent in the last classes, in the last class, we did magnetic Lorentz force. I'm giving just a quick revision of the concept, magnetic Lorentz force. Magnetic Lorentz force. This is magnetic Lorentz force. So if you have magnetic field and a charged particle is moving with some velocity v at an angle theta to magnetic field, then this magnetic field will exert a force on the charged particle. The force exerted by magnetic field on the charged particle is known as magnetic Lorentz force. We calculate magnetic Lorentz force using this expression. It's QE cross B, or you can simply write this as QEB sine theta. That's magnetic Lorentz force. This force is perpendicular to both. This direction of this force is perpendicular to velocity as well as magnetic field. To get the direction of this force, we use right hand thumb rule. See how we apply right hand thumb rule. We take right hand, place our finger in the direction of velocity in this way, and then curl it towards the magnetic field. We place our finger of right hand in the direction of velocity and then curl it towards the magnetic field. Thumb will give the direction. It's very simple. Take your right hand, place your finger along the velocity and then curl it towards the field. Thumb will give the direction of magnetic force now. So if you place a charged particle, or if a charged particle is moving in a magnetic field, then that charged particle will experience a magnetic force. This is the magnitude of force and the direction is given by right hand thumb. The next topic that we will do today, that's Lorentz force. It's based on magnetic Lorentz force only. If you know magnetic Lorentz force, then Lorentz force is easy. So we'll start with Lorentz force today. Okay, can you guess what will happen if you place a charged particle at rest in magnetic field? You take a charged particle and you place that charged particle at rest in magnetic field. What will be the force experienced by the charged particle?
Zero.
Zero. Charged particle will experience force only if it is moving. If your charged particle is at rest, then force would be zero. You will experience force only if your charged particle is in motion. Now, for Lorentz force, we have both electric as well as magnetic field. So if a charged particle, is moving in a region having both electric and magnetic field, so you have a charged particle, it's moving in a region and that region have both electric as well as magnetic field. So charged particle may experience both electric and magnetic force electric and magnetic force So the charged particle will experience both. It will experience electric force as well as magnetic force. Net force on charged particle is Lorentz force. So the net force acting on the charged particle is Lorentz force. That's the Lorentz force. So Lorentz force means sum of electric and magnetic force both. So the electric force which is acting on the charged particle, electric force you can write as Fe, which is equal to QE. In the same region, magnetic field is also present. So you can write magnetic force as FB, which is Q V cross B. The net force F is sum of both electric and magnetic force. Net force is the sum of both electric force as well as magnetic force. So you can say that net force is electric force, which is QE, magnetic force, which is QV cross B. You can write this as F is equal to Q. It's electric field plus V cross B. This is F, which is QE plus V cross B. So this force is known as Lorentz force. So when we say magnetic Lorentz force, that means electric field is absent. If you say that electric field does not exist, then the force experienced by the charged particle is purely magnetic. That we call magnetic Lorentz force. But if you have both electric field as well as magnetic field, then the particle will experience both electric force as well as magnetic force, and that is known as Lorentz force. Note it down. Is it clear? Malia, Mariam?
Yes, sir. Yes, sir.
Shazada?
Yes, sir.
So after a very, very long time, you all 8 are present in the class. It's a very long time. I have seen the full strength of class. No, Noor. It's an external electric field. This E is external electric field. Huh? External electric field. $8:40. Okay, it's a prayer time. Okay, so it's the namaz time, I guess, in Bahrain.
Yes, sir.
It's Maghrib.
Yes, sir.
Okay. So okay, let's take a break for, then we will continue. Huh? Continue after 5 minutes. Meanwhile, we'll continue after 5 minutes. I think. Okay, just note it down.
Sir, can you scroll up for a bit?
So Lorentz force means both The sum of electric and magnetic force acting on the charged particle is Lorentz force. Now we'll see how to calculate this Lorentz force. But for the numericals of Lorentz force, you should know the direction of both electric force as well as magnetic force.
Second scroll up. Yeah.
Just try to recall what was the direction of electric force. We did this in chapter number 1. The direction of magnetic force we did in last 2 classes, but the direction of electric force was in electrostat, chapter number 1. Just try to recall how we get the direction of electric force, how we get the direction of magnetic force. You will be using both the concepts simultaneously. So to solve problems of Lorentz force, you should know 3 concepts: the direction of electric force, the direction of magnetic force, and also cross product in Cartesian form. You should know all these 3 concepts to solve these type of problems. So first of all, let's recall the direction of electric force. So direction of electric force depends upon the charge of the particle. If this is electric field and charged particle is positive, then this positively charged particle will experience force in the direction of field. Next, this is field, and that's negatively charged particle. The direction of force on negatively charged particle is opposite to that of field. That's it. This is how we decide the direction of electric force. For positively charged particle, the direction of force is in the direction of field. For negatively charged particle, the direction of force is opposite to that of field. Direction of magnetic force. For direction of magnetic force, we use right-hand thumb rule. We have discussed this right-hand thumb rule in previous classes. Like if this is your magnetic field, it's a charge Q, it's moving with some velocity V at this angle theta. Apply right-hand thumb rule, Fatma, and get the direction of force. Yes, Fatma, what's the direction of magnetic force?
Downwards.
Downwards or inwards?
Inwards. Inwards.
Inwards. Nah. Place your finger along velocity and curl it towards magnetic field. Thumb is going inwards. So direction of magnetic force is inwards. This is the direction of magnetic force. This is for a positively charged particle. But instead of positively charged particle, if you have a negatively charged particle, this is magnetic force field. This is negatively charged particle. We have discussed this result in the previous class. Right-hand thumb rule will give inwards. But if particle is negative, then the actual direction will be outwards. Outwards means dot. Cross means inwards. Next. Now the first concept that we will use, second concept, third concept is the concept of cross product. You should remember these results like I cross J is K, J cross K is I, K cross I is J. if we reverse the direction, like means if I write J cross I, then it will be minus K. We are doing this second time in this session. For the first time, we did cross product in chapter number 1. When we were doing torque on a current, torque on a electric dipole in electric field. Then we have revised cross product. I'm doing it again this time. So this is K cross J, it's minus I. If you reverse it, like instead of I cross K cross I, if you take I cross K, then it would be minus. For problems of cross product, you should remember these results also. Note it down, then we'll do some numericals. Yes, Noor, we will add E and V cross B using vector addition. But in almost all the numericals, you will get E, V, and B in Cartesian form. So that would be easier to add. Huh?
Yes, sir.
Very rare, like you would be using parallelogram law, triangle law. In majority of cases, you'll be having I cap, J cap, and K cap. So you will be adding them directly. Okay, we'll do two numericals on Lorentz force. The first question is, a particle of 2 coulomb is moving with velocity v equal to I cap minus 2j cap in a region having electric field is equal to 2I cap minus 3j cap Newton per coulomb, and magnetic field B equal to I cap minus j cap minus 5k cap Tesla. So you have velocity, you have electric field, and you have magnetic field. Calculate net force. So for net force, you will be using this relation that net force is Q E plus V cross B. But you need V cross B. For V cross B, we will use the concept of determinant, cross product in Cartesian form. So this is the value of V. V is I cap minus 2j cap. There is no k cap term, that means 0 k cap. And your B is I cap minus j cap minus 5k cap. Now we have to solve this cross product. To solve this cross product, we will make a determinant first. We will make a determinant here. The first row of the determinant is I cap, j cap, k cap. Second row, I cap, the coefficient of I cap is 1. The coefficient of j cap is minus 2. The coefficient of k cap is 0. So it's 1, minus 2, 0. For B, coefficient of I cap is 1, j cap is minus 1, k cap is minus 5. 1, -1 and -5. So this is how we make determinant. Then you have to open this determinant. So to open this determinant, see, first take I cap. When you take I cap, eliminate the row of I cap and the column of I cap. You are left with just -2, 0, -1, -5. So do this multiplication. Multiply -2 with -5 and then -1 will 0. So you will write this as this is -2 into -5 minus -1 into 0. This is how we open cross product. Next term, minus j cap. When you take j cap, eliminate the row of j cap. This was a part of class 11 syllabus, how to solve cross product in Cartesian form. Eliminate the row of j cap and eliminate the column. Sania, which terms are left? Sania, if I eliminate this row and this column, then I'm left with how many terms I'm left with?
I cap and K cap.
See, I cap, eliminate, this row gets eliminated and this column gets eliminated. Sania, this red line here and this red line here means this row is not there, this column is not there. So what terms we are left with? 1,
1 into
-5, 0, 1 and -5. Very good, Sania. 1 into -5, very good.
-1 into 0.
1 into -5, very good. -1 into 0, perfect. Now let's take the third term, K cap.
1 into -1, -1 into -2.
Very good. So there's this row and this column will eliminate. So you'll be left with 1 into -1 minus 1 into -2. So now we have 10.
So why did we take minus j?
The second term in determinant is negative, Ahmed. When we open the determinant, the second term comes out to be negative. So that's 10 minus 0 minus j cap. It's -5 minus 0 plus k cap -1 plus 2. So we have 10 I cap plus 5 j cap plus k cap. So this is V cross B. So once you have V cross B, then rest of the calculations are trivial. Like you have V cross B here. I call this as equation 1. Let's call this as equation number 2. And E is, how much is E? E is this, 2I cap minus Tj cap. And what do you need? You need Q. Q is 2 Coulomb. Let's call this as equation number 4. Now substitute 2, 3, 4 in 1. I won't solve it further. Just put these values in this equation and get the value of force. Note it down and tell me what's the value of force. Okay. Fine, Abdullah. We'll check. Yes, Abdullah, we can add them. Yes. Okay, Amalia. So I get answers from Abdullah and Amalia. Shazada, Ahmed. Okay, now answer from Noor also. We will check whether the answers are correct or wrong, but at least report your answers. Fatma, Mariam,
Sir, can you scroll down for a bit?
Okay, Fatma. Sania, Mariam, your answers. So now I have answer from Abdullah, Amalia, Noor, Fatma. Ahmad, Shahzada, Sania, and Mariam. You are left.
Sir, 1 minute.
Shahzada, are you calculating?
Yes, sir.
Do it fast. Okay, Fatma.
Sir, what is equation number 1? That F is
This one.
equal to
E plus V cross B, yes.
yes, sir.
Okay, Mariam. Now, Ahmad and
Yes, sir.
Shahzada, you two are left only. Everyone else have answered. Okay, Sania, good. Okay, so force is Q, the value of Q is 2. E plus E is 2I cap minus 3J cap plus V cross B. V cross B is 10I cap plus 5J cap plus K cap. 5J cap plus K cap. So this 2I cap plus is 12I cap. 3J cap plus 5J cap is plus 2J cap. So the force is 24I cap plus 4J cap plus 2J cap. So Sania, you were missing few terms, huh? Yes, Mariam was correct. Fatma was also missing some terms. Noor was correct. Amalia is correct. Abdullah is. Shahzada, is it clear now?
Yes, sir.
So that's the first type of question that you can get on Lorentz force. The second type of questions which are important are on predicting the direction of electric force and magnetic force. The next type of questions are based on prediction. So let's. So the question says, this is x-axis. This is y-axis. This is z-axis. So you have a positively charged particle. This particle is moving with certain velocity parallel to x-axis. There is some electric field parallel to y-axis. So positively charged particle experience force in the direction of electric field. So this plus Q will experience force in upwards direction. Yes, Fatma. These are the types of questions on Lorentz force, right? So this positively charged particle will experience force in the direction of field, in the upwards direction. It will go in the upwards direction. So the question says electric field exists along x-axis. Sorry, x-axis. Electric field exists along y-axis. This is the direction of electric field. A charged particle enters with velocity v, with velocity v parallel to x-axis, parallel to x-axis. Predict the direction of magnetic field so that charged particle may pass undeflected. We need the direction of magnetic field so that this charged particle pass through this region undeflected, means no deflection, without any deflection, this particle passes through this region. So to get the direction of magnetic field, first of all, decide the direction of electric force. What would be the direction of electric force? Okay, let's do it together. Huh? Amalia, can you predict the direction of electric force on the charged particle?
Yes, sir. We can.
Yes, what would be the direction of electric force?
90 degree.
90 degree to what? This is the direction of electric force. Huh? Electric field is acting along y-axis. I'm asking about the direction of electric force. It will act along x-axis, y-axis, z-axis. Which direction?
Y-axis.
Why y-axis, Amalia?
Because the current is...
No, it's not about current. See, read this statement, Amalia. Direction of force on positive charge is same as that of electric field, and direction on negative charge is opposite to that of electric field. So answer this question. What's the direction of electric field here, Amalia?
It's on y-axis.
Y-axis. So in which direction this positive charge will experience force? Yes, Amalia. Okay, I'm writing this statement. I'm writing this complete statement. So positive charge will experience force in direction of field negative charge will experience same force in direction opposite to field. So if you have a positively charged particle, then direction of force is same as that of electric field. For negatively charged particle, it's opposite to that of electric field. Amalia, so this is the direction of field now. Now tell me, what should be the direction of force?
The direction will be in y-axis.
Yes, it will be y-axis. Now, why it will be y-axis?
Because of the positive charge goes along the direction.
Yes, because positive charge goes along the direction of electric field. Now, there is some magnetic force acting on the particle. Fatma, can you predict the direction of magnetic force so that net force on the charged particle is 0? Fatma, can you predict the direction of magnetic force so that net force is 0? I'm not asking about field. I'm asking about magnetic force only. Yeah.
Opposite to that of
Opposite to that means along which axis?
Z.
Y, Z.
X.
This is X.
Mhm.
No, this is negative Y. Na?
Negative Y.
So magnetic force should act in negative Y axis. So I'm writing the complete story. These are very, very important type of questions. When you look at previous year's papers, you will find many questions from this chapter based on this Lorentz force. And the most of the questions are in this term, these conceptual questions. So let's first write that electric force is acting in upwards direction. Electric force is along. Yes, Abdullah.
Sir, like why we're taking the force to be as 0? Like why
Because
we're taking that force to be 0?
it's given in the question. So that charge particle may pass and deflect.
Okay, sir.
You have to predict the direction of magnetic field so that the net force on the charge particle is 0. So electric field is along positive y-axis. Electric force, sorry, is along positive y-axis. So you can write that net force will be 0 only if magnetic force is opposite to electric force. Magnetic force is opposite to electric force. That is along negative y-axis. So net force, the condition for 0 net force is the magnetic force, the direction of magnetic force should be opposite to that of electric force. Now means magnetic force should act along negative y-axis. Now you have the direction of magnetic force, but you have to predict the direction of magnetic field. Direction of magnetic field. So to get the direction of magnetic field, you can use following concepts. Let's check, Noor. We'll check it. For direction of magnetic field, we'll use following concept. The first thing is, I'm representing magnetic field by B. Magnetic field should be perpendicular to electric field, first thing. To predict the direction of magnetic field, you should remember this concept. First, B should be perpendicular to E. B means magnetic field should be perpendicular to electric field. Second, magnetic field cannot be parallel to velocity. Because if it is parallel to velocity, then force will be 0. You need some magnetic force. So while calculating the direction of magnetic field, remember these two results. B should be perpendicular to E and B cannot be parallel to velocity. Now let's check. What options do we have? Magnetic field can act along x-axis, y-axis, z-axis. Now we have 3 options, 3 possibilities. We will rule out 2 of them by using these 2 logics. So, Abdullah, can magnetic field exist along x-axis for this particular case we are solving? Why not?
Sir, because it will be perpendicular to velocity. Oh, sorry, parallel to
It can't be. because it can't be parallel to velocity. Velocity is along x-axis, so
Yes.
magnetic field cannot be along x-axis, not possible. See, in this type of questions, no one will ask you to write the complete explanation, but you should write the complete explanation so that during revision you can recall these logics. It's not possible along x-axis because of this result, this particular result. Because of this result. Okay, so Shahzada, can magnetic field exist along y-axis? This is the diagram. Huh? Can magnetic field exist along y-axis, Shahzada?
No, sir.
Why not?
Sir, because for direction, it should be parallel
It should be parallel to what?
to velocity.
No. Read this statement, Shahzada. For direction of magnetic field, the first thing,
Should be perpendicular.
to what? E stands for electric field.
Yeah, electric.
B should be perpendicular electric field. Now, second statement says B can't be parallel to velocity. What's the direction of electric field here?
It's upwards.
Upwards. In terms of axis, Shahzada.
So
Electric y-axis. And the statement here says B should be perpendicular to E. So
Yes.
if electric field is along y-axis, can magnetic field exist along y-axis?
Yeah, sir. You said.
No.
Can.
No, because magnetic field should be perpendicular to electric field.
Perpendicular. Should be perpendicular.
If electric field is along x-axis, y-axis, then magnetic field cannot be along y-axis. It should be perpendicular.
Yes, sir.
This is a statement. So this is not possible. Sania, are you getting it? Why magnetic field can't be along y-axis? Because magnetic field should always be perpendicular to electric field. It cannot be in direction of electric field. So we're left with only z-axis. But for z, we know that magnetic field is along z-axis. But for z-axis, we have two possibilities. One is positive z-axis, another is minus z-axis. For positive z-axis and negative z-axis, we have to use hit and trial method. So for hit and trial method, let's assume out of plus z and minus z, one is the correct answer. Out of these two, one is the correct answer. Let's assume that magnetic field is along positive z-axis. Let's assume that this is along positive z-axis. This is x-axis, this is y-axis, this is charge particle, this is the direction of velocity, and this is z-axis. Now, assuming that magnetic field is along z-axis. Z-axis means outwards. Apply right-hand thumb rule and get the direction of magnetic force. Ahmed, what will be the direction of magnetic force? Apply right-hand thumb rule and get the direction of magnetic force. Take your right hand, place your finger along velocity and curl it towards magnetic field. Where is your thumb going, Ahmed?
Inwards.
Inwards? You're using right hand or left hand?
Right hand.
Right hand? Okay, let's ask someone else. Mariam, apply
So,
right hand.
fingers in direction of velocity, right?
Yes. And curl it towards the magnetic field. Magnetic field is outwards.
Outwards. Then it will be outwards.
Outwards. Okay. Let's try with someone else. Mariam,
Yes, sir.
apply right hand thumb rule and get the direction of magnetic force. Take your right hand, place your finger along velocity and curl it outwards along the magnetic field. Where is your thumb going?
Sir, inwards.
Inwards. Okay. Fatma, what's the direction of magnetic force? Fatima. Fatima, I can listen you. You're not right. Yes, yes, yes. Where this will act? Direction of force is
Z-axis.
Z-axis. Ahmed, no, Abdullah, what's the direction of magnetic force?
Sir, outwards.
Outwards. Noor, direction of magnetic force?
Downwards.
Downwards. Yes, the exact direction is downwards. Let's learn right hand thumb rule again. Take your right hand and do it in front of your camera. Take your right hand, place your finger along the direction of. Do one thing first. Draw this diagram in your notebook fast. We'll copy the rest of the question later, but first draw this diagram in your notebook. That Q is along x-axis and B is along z-axis. Z-axis means perpendicular to your copy. We will learn right hand thumb rule first. Take your right hand, place it along x-axis, means in the direction of velocity, and curl it outwards. Now tell me, where is your thumb going? Amalia, Fatma?
Downwards.
Downwards now. Amalia, where's the thumb going?
Thumb is going to the right side.
Thumb is going to the right hand side? No. Place your finger along x-axis and curl it outwards. In this way.
So the finger is pointing towards me.
Fingers, whose finger? Your finger?
Yes, sir.
It should
I mean
point in the downwards direction.
Yeah, the down of the notebook.
Down of the notebook, right?
Yeah.
That's correct. Means negative y-axis, right?
Yes, sir.
Yes,
Negative y-axis.
Yes, sir.
Sania, you're getting along negative y-axis? Just place it along x-axis and curl outwards. Thumb should go in downwards. Amalia, are you getting downwards direction now?
Yes, sir.
Mariam? You're getting downwards or inwards, outwards somewhere?
Down.
Downwards. So this is how we apply right hand thumb rule. We place a finger in the direction of magnetic field, curl it outwards, thumb will go in downwards direction. So that's the direction of force. Huh? Force is acting in downwards direction. Now back to this question. So for this direction of magnetic field, the direction of magnetic force is downwards. And let's check. In the initial discussion, we have predicted that direction of magnetic force should be along negative y-axis only. So this direction, if magnetic field is along z-axis, then magnetic force is coming downwards direction. It's coming in negative y-axis. Means if magnetic field is along z-axis, we are getting the correct direction of magnetic force. Means this is the right answer. This is the right answer. But let's assume, check the second possibility also, that B is along negative z-axis. This is x-axis, this is y-axis, this is z-axis, this is the direction of velocity, this is the direction of magnetic field. When I draw this direction, that doesn't mean like diagonally, that means inwards into the plane of your copy. Draw it again in your notebook. Draw this thing again in your notebook. Draw this thing again in your notebook. Apply right hand thumb rule now. Where's the thumb going?
Upwards.
Upwards, okay? And what about the rest?
Sir, upward.
Upwards.
Upwards, okay? Amalia, Fatma?
Upwards.
Everyone is getting upwards now?
Yes, sir.
See, if you don't understand right hand thumb rule, then in chapter number 4, almost 50% of numericals you can't solve without right hand thumb rule. And chapter number 6 is again based on chapter number 4. weightage of chapter number 5 is very small. It's negligible, but chapter number 6 have a major weightage, and chapter number 6 is again based on right hand thumb. If you don't understand right hand thumb rule, you can't do chapter number 6 also. So this is how we'll do it. We'll put our fingers along the velocity, which is along x-axis. You can put your fingers over your notebook. Like this is, you place your finger in the direction of velocity and curl it inwards now into the plane of your copy. Thumb will go upwards. Means force is going upwards. Is it clear, everyone? Shahzada, are you getting upwards now?
Yes, sir.
So force is going upwards. But what was the original direction of force that we were predicting? We need force in downwards direction. But if we take magnetic field in inwards direction, then the force is upwards. Is this the correct direction of magnetic field, Shahzada?
So it's
Is this direction correct or not? This is our assumption. We have assumed that magnetic field is along negative z axis. Is this assumption correct? Is this assumption right or wrong?
so it's wrong, right?
Why it's wrong, Abdullah? Shahzada?
So because it's towards the negative z, that's it. Would be.
No. See. Listen. If we consider, listen very carefully. Shahzada will ask again. If magnetic field is along negative z axis, then the magnetic force that you are getting is along y axis, right? You are
Yes, sir.
getting magnetic field along, force along y axis. But the direction of force that we need is downwards. See, electric force is acting in upwards direction. Magnetic force can balance electric force only if it is acting in downwards direction. So the direction of magnetic force that we need is along negative y-axis. We need magnetic force along negative y-axis. But from this direction of magnetic field, the direction of magnetic force that we are getting is along positive y-axis. We need it along negative y-axis, but we are getting along positive y-axis. That's why this assumption is wrong. This assumption is not correct. Yes, Shahzada, did you get it?
Yes, sir.
Explain it again. Why is this is wrong?
So because of that, we need it in the positive z direction, not in the negative. That's it.
What we need?
Electric field.
What is this, Shahzada? FB. What is this? Okay, let's do one thing. Note it down. Shahzada, don't get confused. There are 4 directions here. One is direction of electric field, which is given. One is direction of electric force. Another is direction of magnetic force. Another is direction of magnetic field now. Okay, everyone, just note it down. Then I will start cross-questioning. Shahzada, I'll come to you again. Huh? Just note it down, write each and every statement. Tell me if you have doubt in any of the statements.
Okay,
It's
sir.
a very, very important question. You have one full device which is based on this expression. There is one device which is known as velocity selector. That device is based on this only. Note it down and keep telling me if you have any doubt.
Yes, sir.
Okay. Shazada, read each and every line very, very, very carefully. Where is magnetic force? Where electric force? Shazada, any doubt?
No, sir. Okay.
I will ask those questions again. Lorentz force seems a very small topic, but standard of questions is very good here. Okay, so Mariam, thumb is indicating the direction of force. We have written right hand thumb rule here. Na? Place your finger of a right hand direction velocity and curl it towards magnet. Thumb will give direction of magnetic force. Okay, Mariam?
Yes, sir.
Okay, Shahzada. So what is the final answer? Magnetic field is along positive Z axis. Magnetic field along positive z-axis. So, Shahzada, why this assumption that magnetic field is along negative z-axis wrong?
So because in the other figure, that one is at a negative y-axis.
Which one is along negative y-axis?
The other figure, that other
Which quantity is along negative y-axis?
the velocity one.
Velocity is along negative y-axis. See this diagram. What is this?
Force.
What?
Force.
Which force?
Magnetic force.
And in this diagram, if we take inverse direction, then what's the direction of magnetic force?
It will be on negative, positive z-axis.
Positive y-axis. Huh?
Positive y-axis.
If we take magnetic field to be along negative z-axis, then magnetic force is along positive y-axis. But we need magnetic force along negative y-axis. That's why this is wrong. Magnetic field is along positive z-axis. So it's usually a 2-mark question. You just have to mention the direction of magnetic field. But to arrive at this result, you have to follow this whole prescription. So this detail is very important. There's no need to write this detail in your exam, but you should at least know this detail. Without this detail, you cannot arrive at the correct answer. So that was about Lorentz force. After Lorentz force, the next is force on a current carrying wire. The next topic is force on a current carrying wire in magnet. Force on. But before starting this, I again need some topics of current electricity. Yes, Noor, if magnitude of magnetic force is greater than this, then it will deflect, right? For the next section, I will use few concepts of current electricity. The one is the concept of drift velocity. Does anyone remember drift velocity? What was drift velocity? Sania? Do you remember what was drift velocity? No. Ahmad, do you remember what was drift velocity? No.
Yes, sir.
You remember. What is drift velocity?
Yes, sir. The current passing through a cross-sectional area, I guess.
No. Noor, what is drift velocity?
So the velocity with which the free electrons are drifted towards the positive end of the conductor under the effect of electric field.
Right. So drift velocity is the velocity with which electrons move in a conductor. If you have a conductor, then when you apply connect battery to this conductor, then electrons will move towards the positive end of the conductor with a velocity which is known as drift velocity. So in a very, very simple language, it's the velocity with which electrons are moving inside a conductor. Velocity with which electrons move. That simple velocity is drift velocity. Then we have derived a relation between current and drift velocity. So does anyone remember the relation between current and drift velocity? We have derived a very important relation between current and drift velocity. Yes, Noor, what was it?
NPA. VD.
Very good. E is electronic charge, A is area. What is N here, Fatma? Do you remember what's N? No. Mariam, do you remember what is N? Small n here? Mariam.
Sir, electron.
Electron N. No.
So number of free electron.
Number of electrons per unit volume.
Number of Yes, number density, number of electrons per unit volume. Number of electrons in unit volume is small n. So that's small n number of electrons per unit volume. So this is the concept of drift velocity that we will be using. And one interesting thing, if electrons are going to the left hand side, then current is going to the right hand side. Current and motion of electron is opposite. The direction of current is exactly opposite to that of motion of electrons. So let's solve this question. Force on a current carrying conductor. Remember this result. I will use this result in the next section, that current and velocity of electron are in opposite directions always. So force on current carrying conductor in magnetic. This is again magnetic force that we are calculating. Earlier we calculated magnetic force on a charged particle. Now we will calculate magnetic force on a conductor. That's the difference in two calculations. So this is your magnetic field. This is the magnetic field. In magnetic field, we placed a very thick conductor. We placed a current carrying conductor like this way. We place this current carrying conductor in the magnetic. This conductor is carrying some current I. Length of the conductor is L. The area of cross section of the conductor is A. So L is the length of conductor. This area of ends, this area is area of cross section. And I is the direction of current. Current is going in this direction. This is the direction of current. So, Sania, can you predict the direction of motion of electrons? If current is going in this direction, then what will be the direction of motion of electrons? Yes. Sania, direction of current is given. Not upwards. No, Sania. Fatma, can you guess the direction of motion of electrons? Fatima.
Yes, sir.
What will be the direction of motion of electrons? If direction of current is given, this is the direction of current. What will be the direction of motion of electrons?
Direction of current.
Opposite to the direction of current. Electrons move in a direction which is opposite to that of current. We just have discussed that if current is going to the right, then electrons are going to the left. Current and motion of electrons are in opposite direction. Sania, why I am considering that electrons are moving in this direction? What's the logic behind this result? If current is going in this direction, then why we are taking the current electron to be in this direction? Remember this result, then direction of current is opposite to that of motion of electrons. We did this thing in chapter number 3. That direction of current is opposite to that of motion of electrons. current and motion of electrons are in opposite direction. Okay. So I is the direction of current. We have one more thing, that is N. N is number density of electrons. Number density means number of electrons per unit volume. Okay, we can calculate the volume of the conductor also. Amalia, if area's length is given, then can you calculate volume of conductor? Amalia. Amalia, if length and area of cross section are given, can you calculate the volume of the conductor? Fatma, can you calculate the volume? Okay, Amalia, you're responding. Yes, yes, Amalia. What's the volume of conductor? Area is given, length is given, Amalia. How will you calculate the volume?
Area by length.
Area multiplied by length. That's the volume of conductor. Small n is number of electrons per unit volume. I need total number of electrons. Shahzada, how will you calculate total number of electrons? Shahzada, how would you calculate the total number of electrons?
So, so I asked.
You have small n, Shahzada. Just listen. These are the number of electrons in unit volume. Means in 1 meter cube volume, the number of electrons small n. I'm asking about the number of electrons in volume V. How do you calculate it? The question is like, Shahzada, I'm saying that number of electrons in 1 meter cube, we have 10 electrons. In 20 meter cube, can you calculate the number of electrons?
So it will be 200.
How do you calculate 200?
So just unit vector into that.
Use the same logic here. Small n is number of electrons in unit volume. So what will be the number of electrons in volume V? Yes, Shahzada, how will you calculate it? Number of electrons in volume V.
Sir, the total number of electrons.
I need total number of electrons. How would you calculate total number of electrons?
So I into A.
What is I?
That's
What is I?
direct of
What is I here, Shahzada?
the current.
And what you are supposed to calculate?
You are supposed to calculate the electrons.
Total number of electrons.
Yes.
What is small n?
It's the density of the electrons.
What do you mean by density?
Mass by volume.
Just number density. Just read this statement. What's number density? Read this statement, Shahzada. What do you mean by number density?
So it's NV, like density into number of.
Just first tell me, what do you mean by number density, Shahzada? Just read this statement and tell me, what do you mean by number density?
Number of electrons per unit.
Per unit volume. Unit volume means 1 meter cube, right?
Yes.
I'm asking about the number of electrons in V volume. How will you calculate it?
So NAL.
So multiplied by V, right?
Yes, sir.
And V is AL. Shahzada, Nishkarsh will contact you regarding some extra classes. Huh? So for the next 2 weeks, you'll be coming to some extra classes, some backup classes.
Sir,
Fine?
I also need some.
Sorry?
Sir, I also need some.
Yes. Who is saying? Ahmed.
Sir Ahmad, yes, sir.
So Shahzada, Nishkarsh will call you and just set the timings for those extra classes. I'm not taking those extra classes. There's a separate team for that thing. They will call you for Viva and they will help you in numericals and theory also. Set the timings for them. So the total number of electrons is number of electrons per unit volume multiplied by volume. That's NaL. Okay, now this electron is moving with a velocity which is drift velocity. Vd is drift velocity, velocity with which electrons are moving. Drift velocity of electrons. Consider electron as a charged particle. Electron is a charged particle which is moving in this magnetic field with a velocity Vd. So it will experience a magnetic force. Magnetic force, this magnetic force. This one. So you have an electron which is moving with some velocity in a magnetic field B. So this electron will experience a magnetic force. So magnetic force on each electron. You know that charge of electron is minus E. Velocity of electron is Vd, drift velocity. Magnetic field is B. Tell me the expression for the magnetic force on each electron. Will tell Ahmed. What's the expression of magnetic force on each electron?
Force on each electron.
You know the charge on electron, you know drift velocity, you know the expression of magnetic field. I'm just asking about the expression of magnetic force, nothing else. Charge of electron is minus E, drift velocity is Vd, magnetic field is B. I'm asking about the expression of magnetic force only.
So what is magnetic field?
B.
B. Okay. V E E into Vd into B.
Very good.
Like E bracket
Minus E
Vd into B.
Vd cross B. Very good. This is you are using just Lorentz force, na? Magnetic Lorentz force only is minus E Vd cross B. Okay. That's my first equation. This is force on one electron. Noor, what will be the total force on all electrons? How many total number of electrons are there, Noor?
NaL.
NaL. So what will be the total force on all electrons?
NaL into minus C into Vd into B.
Good. So I can write this as N into Fb. Huh? Force on one electron multiplied by total number of electrons. So this is force on one electron, Fb, small fb, this one. This is force on one single electron. You have total n electrons. So the total force on all electrons will be N into Fb. Let's call this as equation number 1, 2. Let's call this as 3. And let's call this as 4. Let's substitute 2 and 3 in 4. When you make these substitutions, then Fb is N, which is NaL, Fb, which is minus E Vd cross B naught. So we have magnetic force, which is minus of NeAl Vd cross B naught. This is it. Is it clear? Shahzada, Ahmad?
Yes, sir.
Mariam, is it clear? This equation number 5?
Yes, sir.
Mariam, can you find current in this expression? If there is no doubt, then find current in this expression. Can you find current in this equation number 5? Can you combine some terms and make current? You can use, you can refer this thing also, na? This concept also. Yes, Fatma. Can you combine some terms and make current?
NEA and drift velocity.
Very good. So this NEA and drift velocity, this will combine and form current. So you have its the whole this negative sign. Even this negative sign will combine and form current I. We are left with just L. So we'll write this as L cross B now. So this is the force on a current carrying conductor I L cross B now.
So then the negative sign.
Yeah, this negative sign will get absorbed into current. So
Mhm.
current is minus of NEA B. This gets absorbed into current. So it's I L cross B now. If I expand this expression, then I can write this as ILB sine theta. So this is the magnetic force acting on the wire. This is the magnetic force acting on current carrying wire. So the magnetic force acting on current carrying wire is IL cross B now, or ILB sine theta. Next, we will decide the direction of the force. But first, note it down. Note this calculation. It's an important derivation. So if you place a current carrying wire, see, wire is not moving. Wire is stationary. Some current is flowing through the wire. So each and every electron will experience force. Due to the force experienced by every electron, the whole conductor will experience force.
So what is it? A.
Area of cross section of the conductor. Tell me if you have any doubt in the calculation. Okay. Okay, the next is the direction of magnetic force. How will you calculate the direction of
So how
magnetic?
did it become L cross B?
Yeah, see, this N, E, A, and V, D, you can write it as I. This whole term, you are
Yeah.
left with L only. Now, for the cross product, you need two vectors. So what we do is, we make this L length as a vector and take this L into the cross product. Current is a scalar quantity. We can't make current as a vector, but length, if you provide direction to length, then it can be converted into a vector. And direction of length is same as that of current. You can write it as direction of length is same as current. So length and current have exactly same directions.
Yes, okay.
Okay, the next thing. Now I need direction of force. For direction of force, again, we use right hand thumb rule. Use again right hand thumb rule. For right hand thumb rule, take your right hand, place your finger in the direction of current. Along direction of current. And curl it towards magnetic field. Earlier, you were placing your fingers along the direction of velocity. Now place your finger along the direction of current and curl it towards magnetic field. Towards magnetic field. Thumb will give direction of force. Now let's apply right hand thumb rule for this case. Draw this, you have already draw this on your notebook. Now take your right hand. So take your right hand Place your finger along the direction of current. If you have drawn this on your notebook, then take your right hand, place your finger along the direction of current, and curl it towards the magnetic field. Where is the thumb pointing?
Inwards.
Abdullah, you're getting right answer. Inwards. Everyone is getting inwards.
Yes, sir, inwards.
Yes, sir.
Sania, are you getting inwards?
Yes, sir.
Shazada?
Yes, sir.
So you all are getting inwards direction. Huh? So this is how
Yes.
we apply right hand thumb rule. We take a right hand thumb rule, we place a finger along the direction of current and curl it towards the magnetic field. Thumb is pointing inwards. That means direction of force is inwards now. Forces in inverse direction. We'll solve one formula based numerical on this concept and then we will see some modifications. First question. It's very, very, very easy question. Magnetic field is inwards. Huh? This cross is the direction of magnetic field. This is a conductor. Length of the conductor is 10 meter. Current passing through this conductor is 5 ampere. Magnetic field is 2 Tesla inwards. The formula based thing. Just calculate magnitude and direction of force. Calculate magnitude and the direction of force. Calculate magnitude and the direction of force. Do it. Calculate and write your answer in chat. Please write your answers in chat room. Okay, Ahmed. Ahmed also mentioned the direction. Your magnitude is correct. Also mention the direction. Abdullah, magnitude and direction. No. Magnitude is correct, Abdullah, but direction is wrong. Magnetic field is inwards. Noor, magnitude is correct. What about the direction? Fatma, magnitude is correct. Ahmed, direction is wrong. Shazada, magnitude is correct. What about the direction? Draw this thing on your copy. Place your finger along the current and curl it inwards. Magnetic field is inwards. No, Fatma. Noor is correct. Direction of Noor is correct. Yes, Noor. Direction is correct. Amalia, where is your answer? Magnitude and direction both. Mariam, your answer. Sania. Fatma, magnitude is correct, but not the direction. Abdullah, no, Abdullah, it's not correct even now. Mariam, Sania, and Amalia, are you calculating it? Magnitude is fine, but Amalia, direction is inwards, outwards, upwards, downwards. Where is it? Right, Ahmed, it's correct. Sania, what's magnitude? Mariam? Magnetic force is ILB. No, Amalia, it's wrong. Sine theta. Current is 5 ampere. Length of the conductor is 10 meter. Magnetic field is 2 Tesla multiplied by, yes, Abdullah, now you are right. Correct. Nah, Mariam, no. Direction is wrong. Sine 90. Sania, magnitude is correct, but what about the direction? So that comes out to be 100 Newton. Everyone is getting the same magnitude. Magnitude is correct. Now, for direction, do one thing. Draw this thing on your notebook first. No, Mariam. Mariam, magnetic field is inverse, so force cannot be inverse. Yes, Amalia, now it's right. Magnetic field is inverse. Huh? Again, apply right hand thumb rule with me. Take your right hand, place your finger along the current. This is the direction of current along x-axis. And curl it inwards into the plane of your copy in this way. Where is thumb going now? Amalia, Mariam, Fatma? What's the direction of thumb now? It's upwards. This is, some of you have confusion in upwards and outwards direction. See, this is leftwards. Sorry. This is left. This is right. This is up. This is down. When I say out, means out of the plane of your copy. I can't draw out here, so I draw out in this way. Cross means into the plane of your copy. So if you apply right hand thumb rule, where is thumb going? Inwards, outwards. Take your finger, curl it towards the magnetic field. Thumb is going up. So magnetic force will act in upwards direction. Is it clear now?
Yes, sir.
Do one more thing. And please don't make any mistake now. Huh? What this dot means?
Inwards.
Outwards.
Dot means out.
Outwards.
Out of the plane of your copy. This is outwards, out of the plane of your copy. Magnetic field is 2 Tesla. Conductor is placed in this way. As the previous case, it's 10 meter. Current is 5 meter. Calculate magnetic field. Magnitude and direction of force. Calculate both the magnitude as well as the direction of the force. Good, Mariam. That's right. That's you're correct. Sania, magnitude is correct. What about the direction? No, Sania. Apply right hand thumb rule, Sania. It's wrong. Noor, magnitude is correct. What about the direction? No, Sania. Sania, you cannot guess the direction of magnetic force. You have to apply right hand thumb rule. You cannot predict it without applying the rule. Yes, Noor. Direction is correct. Shahzada, magnitude is correct. Ahmed, magnitude and direction both are correct. Shahzada, direction is correct. Fatma, magnitude is correct, but not the direction. Amalia, magnitude is correct, but not direction. Yes, Mariam, direction is correct now. Now it's correct. No, Sania. Now let's first calculate the magnitude, then we will discuss direction. Force is Q V B sine 90. Charge is not
So QLB, right?
ILB.
ILB, yeah.
I is 5, L is 10, B is 2, it's sine 90. So magnitude wise, everyone is correct. It's 100 meters. Now for direction, this means out of the plane magnetic field is coming. Take your right hand, Sania, and place your finger in the upwards direction. Take your right hand and place your finger in this way, upwards. Place your finger in this way, upwards. And curl it outwards. Your magnetic field is coming outwards. Yes, Sania, what's the direction of thumb now?
Sir, it's showing downward.
Your thumb is going downwards. Do it again. Take your right hand. Place your finger in the upwards direction. And curl it outwards. Curl your finger in the outwards direction. Where is your thumb going, Sania?
Outward.
Mine is going in the right hand side direction. This is how we place thumb. This is how we place our palm. Finger is out, upwards and you curl it outwards. The thumb is not going outwards. Thumb is going in the right hand side direction. Are you getting it now?
Yes, sir.
So see, just place your right hand in this way. Don't curl your thumb anyway. Just place it in this way. Don't move your thumb. Just place it in this way, perpendicular to it. Then you place your finger in the upwards direction. Curl it in the outwards direction. Your thumb will go to the right hand side.
Yes, sir.
Okay, note it down. So direction is right hand side, right. In vector form, you can write this as FB is 100 I cap. So that is about force on a current carrying wire in magnetic field. Note it down. The next topic that we will do will use this concept, the force on current carrying wire. Note it down. Is it clear? Force on a current carrying wire in magnetic field?
Yes, sir.
It's right hand side direction. Amalia, Abdullah, is it clear now?
Yes, sir.
Okay, so let's stop here. We'll continue this on. Okay, can we take that Thursday class on Wednesday morning?
No problem, sir.
No, sir.
Yes,
Yes
sir.
or
No
no?
problem. Yes, sir, it's fine.
Yes, sir.
Okay, everyone write your confirmation in chat room. Wednesday morning 10:30 a.m. Please write your confirmation in chat room.
At 10:30 Indian timing or Bahrain timing?
Sorry, Bahrain means 8 a.m.
Okay, sir.
Bahrain 8 a.m.
Sir, but is it possible for you to keep the reminder?
Yes, I'll ask Nishkash to remind everyone.
Yes, sir. Last time.
Amalia, okay. Last time you missed it.
Yes.
And maybe he was sleeping.
Just 1 second somewhere. So, Mariam, you have issue in this timing?
Yes, sir.
You have another class?
Sir, I have chemistry from 1 to 3 and also maths.
1, 2, 3, na?
Yeah, maths is in the morning. I guess.
At what time?
I have to confirm. 1 second.
Well, usually your maths class is from 10:30, as far as I. Okay, Mariam, just do one thing. Just confirm with
Sir, maths is at 10.
maths is at
10.
10 and it's an online class, right?
Yeah. Then you can keep. No problem.
Okay, fine. Maths is at 10, na, so I will finish it up.
Okay.
Okay, Fatma, the issue of Amalia,
Yes,
can
sir.
you attend on Wednesday at this time, 8 a.m.?
Yes, sir. I can.
You can, na? Okay. And else have issues? Fatma, what about you?
It's okay for me, sir.
No problem. Okay. Okay, so the next class is on Wednesday, morning 8 a.m.
Thank you, sir.
Okay, Allah Hafiz.
Thank you, sir.
Yes.
Thank you, sir.